Hello, my name is Nico Geraldo, and this is Creative Assignment 2. I'm going to be doing some friction coefficient testing. So my experiment is to experimentally find the coefficient of friction of a Hot Wheels car axle. So not the rolling friction of the car, but if you were to roll the car, the friction that happens with the little axle that goes through here on the car um, to slow it down. So here are some of the assumptions I made. They don't make a lot of sense right now, but I'll explain them a little bit more later. Um, a lot of these have to do with the length of the rubber band that I used to propel this Hot Wheel car. So here are the equations I used. I used this kinematic, and then from this kinematic I derived an equation for acceleration using the distance that the car traveled and the initial velocity of the car. And then I have a equation for the force of a spring using the spring constant and the displacement of the spring, F equals ma, and then the force of friction using mu, which is the kinetic coefficient of friction in this case, and then normal force. So this is what I was talking about with the assumptions. If you can imagine, actually I can show you real quick. So if you have a rubber band with one finger here, so that my thumb, this is my index finger, I have found a perimeter using the length of this side and this side, the width here, and then the radius of my finger. Um, so this perimeter is my initial perimeter, and then when I pull the car back into this point, I'll get this perimeter, and then I have a little derivation here. But that's what the assumptions were important for, is to find this perimeter and then eventually find the delta right here, which will be this x value. So my setup is I have the rubber band placed here around the 3.5 centimeter mark. I have the car measuring tape, and then I have a little stop with the TV remote and a coffee table. So procedure, place the rubber band around the index finger and thumb, as you can see in here. And then I have it at the base of my fingernail, which I'll show later in the video. Align the front rubber band with the 3.5 centimeter mark on the tape measure. Place toy car in the center of the rubber band slingshot and pull back until the front of the rubber band meets the rear part of the band. So pulling this until it reaches here. So this displacement is just going to be the width. Well, the displacement for the car is just going to be the width, but it's a little different for the rubber band since it's the circumference. Release the toy car and record the rear of the car from the resting position for when it stops. So I have the starting position measured from the rear of the car, so the ending position is also going to be measured from the rear of the car. And then I repeat those steps 2 more times for a total of 3 trials. So I have a little video of me doing the experiment. As you can see, I put the rubber band around my fingers towards the base, and that's just trying to keep the values of W, L, and R consistent, which is pretty difficult to do. And then I line it up in the middle. I also have the front of the band lined up with 3.5 centimeter mark, and then I release the car. There you go. And then on to the discussion of the data. Some important things to say is that the car's weight and the spring constant I found from online sources, and I have those marked in the in my sources. This is because I didn't have a scale in my house that also could measure that. The length of the rubber band I found in 2 different ways. I found it by folding the rubber band to where I just had like 2 strips, and then that gave me this value. So I have my folded length, I multiplied that by 2 to get this. And then I also tried another method of trying to make the rubber band a circle to the best of my ability. I got this diameter, and then I plugged that into the equation for the circumference of a circle, and I got that. So then I averaged these 2 values to get an average length of this. I didn't use this value too much. I just used this mostly to check that my L, W, and R values gave me a initial length that made sense. So as you can see from doing these, so I recorded it from my finger, so it's not super accurate, but it's mostly accurate. This is a little larger than this value, which makes sense because there's going to be a little bit of tension initially, just so then there's no slack. And then when I pull back the car, this is what the stretched length will be, and then this is the delta, so the x that goes into the spring force equation. So, and then I recorded that my launch point starts at 3.5 centimeters, and then I do launch calculations. So, just to save time, that's what they are. I used the kinematic equation to get this acceleration, um, the one I derived. And then afterwards, I have my post calculations or post launch calculations. I have all three trials right here, and then I ended up averaging the force of friction, and then divided it by the normal force that I found up here by just multiplying the acceleration of gravity and this car weight. So this is what I got for my coefficient of friction. So next is error analysis, and there are quite a few places for there to be error. First off, these first two values are values I got off the internet, and since so the weight of the car is just an average weight of like a certain size of Hot Wheels cars, so of course that's not going to be completely accurate for my specific car. K value for rubber band, the rubber band looked very close to the rubber band I had and had similar dimensions. So that's probably close, but not exact. The actual length of the rubber band, of course, changed throughout depending on where exactly I had it on my fingers. So, and same with the length of the rubber band under tension. So none of this is super exact, and I had to use a lot of assumptions to keep them as close as possible. But this overall experiment was to just get a general idea of what the coefficient of friction would be. And then the final and initial position of the car, these were just depending on the where they were on the specific tick on the measuring tape. So connection to airspace, this is actually pretty similar. Launching a fighter jet off of an aircraft carrier is actually really similar to launching a little car with a rubber band because of the propulsion mechanism they have underneath the floor of this. And then to stop it, instead of using friction to stop the plane, because that wouldn't be nearly enough, they use another catching mechanism. So you could do similar calculations, you just have to, the back end of the experiment would be different with, instead of finding friction, you'd find the force of the mechanism underneath the floor. And then these are my sources. This is the source I used to find the weight of the Hot Wheel car. This is the source I used to find the rubber band coefficient. So thank you.